Welcome everybody. Theoretical computer science seminar at Daejeon University. Today our speaker is Tony Huynh from Institute for Basic Sciences in Korea, Daejeon, discrete mathematics group led by Sang-il. What can we say about Tony? PhD in 2009, Waterloo with Jim Gillen. After that, some positions, mainly postdocs. We have some history together. It's great to have you back here, Tony, in Krakow. And we will hear about something new, at least to me, new project. The floor is yours.
Right. Yeah, thank you, Piotrek. Yeah, so as Piotrek said, I've been to Krakow before, but it's been quite some time. So it's a pleasure to be back here. Thanks everyone for coming. So I want to talk about kind of a geometric version of the Erdős-Hajnal conjecture. This is joint work with Carolyn Chun from Maryland, James Douthit from Syracuse, Wenge from LSU, Matthew Crocker, who is, I think, in TU Freiburg now, and Peter Nelson, who's at Waterloo. Okay, so my style of speaking is very slow and elementary, so hopefully it'll be understandable, but I apologize to the experts if it's too slow for you. So let me begin with a very general question, which is, when in mathematics does imposing some local structure imply that something happens globally, right? So just as one simple example, suppose you're a topological space, and I tell you that locally you look like a disk, right? So you locally look like a disk. So, okay, so by the classification theorem for surfaces, if you assume some, mild global assumptions like orientability, then we understand the global structure completely. So if you locally look like a disk, then it turns out that you are a sphere or a donut or a double donut and so on. So this local structure implies something globally. Okay, so this is the theme of the talk. So we want to do this, I guess, for graphs. There's many ways to do it, but maybe the most natural is to use induced subgraphs, right? So there's more than one way, but maybe this is the most natural way. So probably everybody knows this, but we say that a graph G is H-free if it doesn't contain H as an induced subgraph, right? So an induced subgraph, you're just not allowed to delete edges. You can delete vertices, but you can't delete edges. Probably everyone knows this, but let's just go slow. So let's think about P3 free graphs. These are graphs that don't have the three vertex path as an induced subgraph. So what this means is that, every time you look at three vertices in your graph, you should not see that local pattern, right? So if I look at those three vertices, I should not see a path. So maybe I see a single edge. I look at some other set of three vertices, I'm not supposed to see this three vertex path. Maybe I see a triangle, and then maybe for this set of three vertices, it's a stable set. There's no edges or something, right? So locally, I do not have a three vertex path, and it turns out that you can sort of describe the structure of these graphs globally. They're just a disjoint union of cliques. So this is an exercise that you can give your students, right? So these P3 free graphs are exactly the graphs which are a disjoint union of cliques. Okay, so we impose some local structure, and then we got something interesting globally. But you might say, okay, maybe this was just an accident, right? Like maybe this is like a law of small numbers thing that is why we had such a nice structure. So what happens if you forbid maybe a graph on 100 vertices as an induced subgraph? Does something interesting still happen? And that's what the Erdős-Hajnal conjecture says. So it says that actually take any graph, H, your favorite graph H, and it turns out that if you forbid H as an induced subgraph, then something interesting happens globally. What happens is you have a large homogeneous set of vertices. I'll tell you what that means, right? So here large means that it's polynomial, so its size is at least n to the epsilon, where epsilon is a constant that depends on this graph H. And homogeneous just means that, well, it's a clique or an independent set, right? So either all the edges are there or all the edges are not there. So, so maybe it's that, or maybe it's a clique. This is what we're looking for. And I should say that this is something special because this is a property that's not satisfied by all graphs, right? So, so by Ramsey's theorem, you can find these homogeneous sets, but typically they're only logarithmic size, right? So, so once you forbid your favorite graph H, you get much larger homogeneous sets than you would expect from the typical graph. Okay, I should say just interrupt me if anything is unclear. Okay. Okay, so just as a sanity check, let's prove this Erdős-Hajnal conjecture, in the case that you are P3 free, right? So we know the global structure, and the proof is very easy, right? So either one of these cliques is already very large, let's say like square root n vertices, and you're done. So now all these cliques are small, so I just pick a vertex from each of them, and I have at least square root n vertices. So the worst case is if you had square root n cliques of size square root n. Right? Okay, very good. Okay, so right, that was the proof I just gave. And I should say that there's been like a lot of breakthroughs in the Erdős-Hajnal conjecture recently. Like it's kind of a very fast-moving area. You can just go to Paul Seymour's webpage and you'll see new papers appearing every few weeks. But in this talk, I kind of want to stress that for the exact theorem, still quite little is known, right? So, so there are approximate results. There's things that you can do, like you can forbid more than one induced subgraph. But the cases for which we know that the conjecture holds are still quite limited, right? So what is known? So it is true if H is a cograph. So a cograph itself can be described by forbidding induced subgraphs. So the cographs are the P4 free graphs. And this is essentially like the only infinite class of graphs for which we know Erdős-Hajnal holds. Okay, it's true for the bowl graph. So that's the bowl. It's a graph that looks like a bowl. It's true for the 5 cycle, and this was quite a big breakthrough, right? Because so this is sort of the first example where something called the strong Erdős-Hajnal conjecture or the strong Erdős-Hajnal property does not hold. So they really needed some new techniques for this C5. And then recently it was also proved for the 5 vertex path, right? And actually there's some operations you can do to get new graphs for which Erdős-Hajnal holds if you know some graphs that satisfy Erdős-Hajnal. So together, this is enough to say that it holds for graphs up to 5 vertices. So quite limited. Okay, so we have a kind of hopelessly difficult problem. So of course, we want to just make it even more difficult, right? So so let's make this problem even harder by introducing colors. Okay, so so instead of talking about induced subgraphs, I'm just going to talk about colored complete graphs, right? So, so suppose that I have 2 colorings of 2 different complete graphs. So I say that one coloring contains another coloring. Well, you can read that, but it's not really that interesting. It just means that you really contain that small colored clique inside, so you're not allowed to permute color. Yeah, go ahead. These are edge colorings, sort of, right? So the reason that they're edge colorings is that you can use one color to encode edges, for example, and the other color to encode non-edges. So when I talk about colorings of complete graphs, there'll always be colorings of the edge set, and then I'll say that one edge-colored clique contains another edge-colored clique if there's an injection from the smaller clique into the larger clique, such that the set of the edge colors are preserved exactly. That's what that map does there. So just as a simple example, this colored K4 contains like that pink triangle. It really contains it, but it doesn't contain like a blue triangle, right? I'm not talking about just the color pattern. I really want the colors to match exactly, okay? Okay, good. So we use sort of the same language. So if I don't contain a fixed coloring C, then you are C-free, okay? And it'll be convenient to fix the set of, right, so it'll be convenient to fix the set of colors to be like the numbers from 1 to S. So an S coloring is just a coloring where the colors are these numbers. Okay, so now there is a multicolored Erdős-Hajnal conjecture. This is not my conjecture. This is actually a conjecture of Erdős and Hajnal themselves in a different paper. And it just says sort of what you think it does, right? So you take your favorite coloring of a small complete graph, and the theorem says that if you color like a large complete graph in such a way that you avoid this coloring of this small complete graph, then something interesting happens globally. And what happens is that you have a large set of vertices, which I call C homogeneous. So C homogeneous, it's a weird name, but it just means that you avoid some color, actually. Okay, so C homogeneous means there is a large subset of vertices where at least one of the colors is missing. Okay, and large is the same thing as in Erdős-Hajnal. So this is at least a polynomial in N. Okay, right, so this is the picture. I have some large edge-colored complete graph, and what I'm looking for is a large clique that avoids some color. So unless I made a mistake, I think that clique there has no green edge. Okay, so you can check that that is a homogeneous clique. Okay. So this is what I want to do. Why would we want to do this? Well, it's easy to see that like multicolored Erdős-Hajnal implies the classical Erdős-Hajnal conjecture, because all we need to do is if I have some graph H, I just color the edges blue and the non-edges red, right? And if I only use two colors, then homogeneous really means that I'm monochromatic, actually, right? If I avoid some color, but I only have two colors, then I find a monochromatic clique, and this monochromatic clique will either be a real clique in the graph or an independent set in the graph, right? So the two-colored version of Erdős-Hajnal implies the classic Erdős-Hajnal. But this makes it sort of easier to generalize further. So we're going to go even further from graphs to matroids, basically. Okay, so the way to do this is let's think about like what is a complete graph, right? So a complete graph is basically like an ambient space for the set of graphs, right? So a complete graph on n vertices is just a universal graph. It's something that contains all simple graphs on at most n vertices as a subgraph. So in the geometric world, the role of complete graphs is going to be played by the projective geometries. So these are basically right. So these are just things that contain like all representable matroids up to a certain rank, right? So they're defined by just taking the one-dimensional lines. So that's a picture of the Fano-matroid, right? So over the binary field, all I'm doing is I'm just taking all of the non-zero vectors, right? If I have a larger field, then I'll just pick one vector from each one-dimensional line. Okay, so these are the projective geometries. Okay. Okay, and the coloring, so I've colored the edges, but in the geometric world, I just color the points, right? So I've colored the points of this projective geometry. Okay, so what is a clique? Well, in matroid language, a clique is just a closed subset, actually, right? So in the geometric side, a clique corresponds to a subspace, actually, right? So you want to take all the vectors in some subspace, and C homogeneous is the same in both, right? So in the graph world, I want to find a clique that avoids some color. In the geometric world, I want to find some subspace that avoids some color, right? Like that line, for example. I think that line avoids yellow, right? And then just as a technicality, the size of the clique corresponds to the dimension of the subspace, right? So, okay, so with this dictionary, we can now state this like multicolored geometric Erdős-Hajnal conjecture. I'll put it up there, but you don't really need to read that. It's completely clear what this should mean, right? So basically, you take a small projective geometry, that's this PG K-1 Q, you color it in your favorite way, and then the theorem or the conjecture says that if you take a large projective geometry, so this PG N-1 Q, and you color it in some way that avoids this fixed coloring of this PG K-1 Q, then something interesting should happen in that you should have some subspace of large dimension that avoids some color, right? So this is what the conjecture says. Okay. Yep.
Are there any implications between this and the rough conjecture?
Yeah, this is a good question. I would say neither implies the other, it seems. But like we'll see that kind of they're definitely analogous and sort of the same proofs work. One could argue even that the geometric world is kind of nicer because some theorems actually become easier. We'll see that later. So yeah, as far as I can tell, like neither implies the other actually, but they are like definitely analogous. Maybe somehow you could derive the graph result from the matroid one, but this would take some work, I would say. Okay, so so anyway, I have that beta and the epsilon just to, I mean, the beta is not very important, but it is just there to show maybe some tightness results. So if you care about that exact constant in front of the n to the epsilon, that's why the beta is there. But anyway, just think of large dimension, which is a polynomial in n. Okay, so here is the picture. It's hard to draw these kind of large dimensional projective geometries, but so here maybe I've colored the Fano plane, and I have that line in the middle, right? So Peter Nelson spoke about this in Oberwolfach, and I guess Jacob Fox was in the audience, and he asked, hey, like maybe it's possible that you could take epsilon equals 1 even. So this means that not only do you have a polynomial size dimensional subspace that avoids some color, but it's linear, actually. So this seems pretty wild. Like, yeah, I mean, it seems false to me, but we don't have any counterexamples. So I should say, if anyone wants to think about these kinds of problems, like I'm here until the end of the week, so happy to chat about it. So it is possible that epsilon equals 1 holds. This seems kind of crazy, but we don't have any counterexamples. Okay, good. So let me tell you what we proved, right? So our main results, the ones I want to talk about, are for small values, so k equals 2, and the binary case, so q equals 2. So this is very simple. All I'm doing is I'm just coloring the non-zero binary vectors, and I want to find a triangle or a line. So this is what I'm forbidding. So I'm going to forbid some coloring of a line, but there's actually 3 possible colorings of this line that I could forbid. So there's 3 things I have to prove. Maybe the line is monochromatic, so that's the first case. Maybe there's 2 colors that are the same, and the third color or the second color is different, and maybe it's rainbow, right? So these are 3 things that we have to prove, and we resolve like all 3 of these cases. Okay, there's a little bit more in the paper, but this is like right. This is essentially the main result. And I think what is kind of cool is that we use completely different methods so for 2 of these, we use some tools from additive combinatorics, some very heavy machinery. And for the rainbow case, we do something that's pretty combinatorial. So the proofs are completely different. I'll show you both of the proofs, essentially. They're not too difficult. So what we proved is that in the monochromatic case, or the case where you have just exactly 2 colors, the conjecture does hold, and we get epsilon equals like 1/7. So we get this subspace of dimension about n to the 1/7 that avoids some color. And then in the rainbow triangle-free case, we do get this linear size. Oh yeah, go ahead.
What happens if you have 2 colors but they don't appear in this order that you described? Is it the same case?
If you go back to the statement, like I always fix the number of colors. So this we have like S0 and S. So so the number of colors the colors that I use on the small guy are the numbers from 1 to S0, but the colors I use on the big guy are the numbers from like 1 to S, right? So if, say, I just don't use some colors, then I'm done, actually.
Right. I think the question was about ordering, but for projective geometry, ordering doesn't matter.
Oh, yeah. Oh, I see. This thing. Yeah, they're the same, actually. Like this is projective space. So is it okay? Yeah. I mean, these really are triangles. So like for triangles, it's the same coloring, actually. Okay. Sorry. Okay. So right. So in the rainbow triangle-free case, Fox's conjecture does hold. So we get an actual linear bound. And we even get a tight constant in front. So this beta equals 1/3. So you can get subspaces of dimension like n/3, and this is best possible. Okay, so,
you also mean that 3 colors is best possible. So for 4 colors, this does no longer hold.
For 4 colors, yeah, we don't know for sure, I guess. But for 3 colors, like this is the answer. Okay, so let me show you the proofs of all 3 of these. Okay, so I'll do the additive combinatorics stuff first, right? Okay, so let's just have some definitions from additive combinatorics. So suppose I have some subset of binary vectors. So I want something that's analogous to the clique number and the independence number of a graph. So I define, let's say, the clique number to be the dimension of the largest subspace that's contained in my set of points. Okay, and when I say contained here, I'm working in projective space, so I don't care whether you contain the zero vector, but you have to contain all the other points. Okay? So containing a subspace means you contain all of the vectors in that subspace except possibly the zero vector. Okay, so that's the clique number, and then of course the independence number you can define to just be the clique number of the complement. Okay, so this is the dimension of the largest subspace that's not in your set of points. Okay, and so to prove our theorem, we just let the combinatorics, additive combinatorics people do all the heavy lifting. So everyone probably knows, but there was this big breakthrough recently in additive combinatorics by Kelley and Meka about bounds for sets of numbers that don't contain like 3-term arithmetic progressions, right? So this, and so in their body of work, we just extract a lemma that is sort of precisely what we need. So this lemma was basically stated by Hunter and Bohota. So what does the lemma say? It says that, okay, for any collection of binary vectors, like one of two things is large, right? So this says that either the independence number is large, so it's at least like about n to the 1/7, or the clique number of its sum set is large. So if I take x plus itself, then that clique number is large. So one of these two things will happen, and they proved here large means n to the 1/7. Okay, but yeah, this is a very hard theorem. I don't understand it, but for us, we're happy to just use it. We conjecture that this could hold like linear, actually. So with like it could be true that this actually holds with just a linear term, and that would imply again the linear result directly with the proof that I showed you. Okay, but at least we get this n to the 1/7. Okay. Okay, so now let me do the proof, like just assuming this lemma as a black box. Okay, so and this lemma will actually handle like both of these cases at the same time, right? So so this handles the monochromatic and the two-colored case simultaneously. So what do? We want to apply this lemma, and so I'll apply this lemma to the set of red points, right, in my coloring. So the setup is I have this big projective geometry, and it avoids, let's say, like a red line. Okay. So let's look at all of the points that are colored red and apply this theorem of Kelley and Meka. Okay. So it says that one of two things happens, right? So either the independence number of this set is large, and if this is the case, then we're done, right? Because this means that there is a subspace in the complement of X of large dimension, and the subspace does not use the color red, right? Because X is a set of red points, right? So if outcome 1 happens, I'm done immediately, okay? So now we just have to deal with outcome 2. So outcome 2 says that the clique number of X plus X is large, okay? So this means that there is some subspace H in the sum set of large dimension. So all that means, just by definition, is that for every non-zero vector in this subspace, there are 2 points in X that add up to U, right? This is what the sum set is, right? But now you notice that these 3 points are actually a line, right? So so in binary space, three non-zero vectors that add up to 0 are precisely a triangle, right? So what this means is that we're done in either case, right? So, so if my coloring avoids a red triangle, then I know that the color of U cannot be red. Otherwise, I would have this red triangle. And if I avoid this, like two red points and a blue point, I know that the color of U is not blue, right? So, so in the first case, like the subspace H avoids red, and I'm done. And in the second case, the subspace H avoids blue, and I'm done, right? So that's the whole group. So all of the work just goes into this lemma of Kelley and Meka. Okay. Okay. Let me continue. So now let's do the rainbow case, which is completely different. And here the strategy is more combinatorial. So we're going to just prove a structure theorem about the rainbow triangle free colorings of this geometry. So we're just going to classify all of them. We're going to describe exactly what they look like. And once we have the structure theorem, it'll be easy to derive the result. So let's go back to graphs for inspiration. So don't worry, the rest of this talk will just be graph theory, actually, right? So let's go back to graphs for inspiration. So, so here's a question, like what are the colorings of the edges of a complete graph that do not contain rainbow triangles, right? So this is some question, and it has a beautiful answer. So this is a theorem of Gallai. This is a theorem I didn't know before starting this project, but these colorings have been completely classified. They're called Gallai colorings. So the theorem says that if you have a rainbow triangle-free coloring of a complete graph, then it's a blow-up of a two-colored complete graph. Right? So all this means is that, so those thick edges mean that all the edges between like those two blobs are red, and those thick blue edges mean all the edges between those two blobs are blue, okay? And then you can blow up the vertices, and what are you allowed to put inside the blob? Well, you can put any rainbow triangle-free coloring of that smaller complete graph, okay? So you might not think that this is a theorem, but this does have content because you can just reapply the theorem inside each of these blobs, and you'll get like a decomposition of your coloring into like two colored pieces. Yes?
What the property of this big two-colored complete graphs? It has at least order 2 or something more?
There is nothing. So it's just the fact that you use two colors. So for example, if your coloring only has two colors, then your blobs would just be single vertices, right? And obviously any two-colored complete graph does not have rainbow triangles, right? And the same thing can be said here, right? So if you look at this picture, this structure definitely does not contain a rainbow triangle. Is there a laser or something? What is this? Let me try. Oh, wow, okay. So, right, so let's consider like all possible triangles in the structure. If it lives inside one of these blobs, it cannot be rainbow because I told you that each of these blobs is rainbow triangle free. If it lives in 3 different blobs, it cannot be rainbow because I only use 2 colors on the outside here. And if it goes between 2 blobs, it's not rainbow because all of these edges are the same color, right? So this picture certifies that you're rainbow triangle free, right? Okay, so when I gave this talk, I went out to dinner like afterward with, I think Yuval Filmus, and he asked me how to prove this theorem, and I wasn't able to prove it over dinner, but I thought about it like that night and figured out how to do it. So now I just put it in my talks as a as a source of pride. So I guess as an aside, let's just prove this theorem. Okay, so the key lemma is that if you have a rainbow triangle-free coloring of a complete graph using at least 3 colors, then at least one of the color classes is disconnected. Okay, and by disconnected, I mean take all edges of that color, but also take all the vertices. So these the red subgraph is always a spanning subgraph. So if it has isolated vertices, it's disconnected in my view. And the key lemma is to prove that actually there will always be some color class that is disconnected, as long as you use at least 3 colors. That's easy to prove. You can do that by induction. Okay, so I won't do that part. But assuming this key lemma, you can prove Gallai's theorem quite easily. So this is what I will show you. So let's look at one of these red components here. And because I'm rainbow triangle free, I know that the edges from that vertex to those 2 other vertices must be the same color, right? They're not red because these are the red components. So maybe they're both blue, right? So this could happen. And then I use the fact that this is a component, so it has a spanning tree. And that means that actually all of the edges from this vertex to this component are blue, right? Because I just use the connectivity here. So now I know that for every vertex here, all of its edges are the same color, right? And then I can do this for another vertex, and I claim that those are also blue. The reason is because you can do this argument from both sides, right? So I know that they're all the same color. Maybe they're not blue, but actually they have to be blue because I can just run the argument from the other side, actually. So now I've actually reduced to the case where between any of these red components, all of the colors are the same, right? So that thick blue edge means like all of those things are blue. And now I'm just done by induction, right? So if there's only 2 colors, as we discussed before, the theorem is true. And otherwise, you just apply the key lemma and apply induction, right? So, okay, good. Okay, so now, okay, so the story is that once you have the structure theorem, it's easy to prove like rainbow Erdős-Hajnal results, right? There's a nice theorem of Fox, Gernsbaum, and Pak that does just that, right? So what does their theorem say? It says that, okay, if you take a 3 coloring of a complete graph that does not have a rainbow triangle, then it has a very nice decomposition. So their theorem says that actually you can decompose your graph into 3 subgraphs, G1, G2, and G3, such that, so each of them is a spanning subgraph. They're edge disjoint. And the key property is that each of them is a cograph. Okay, so, right. So I can also prove this. Maybe this is the only proof that I'll do on the board. The proof is also on the slide, but maybe it's too fast. So I'll just do the proof here. Okay, do I have colors? Maybe red, blue, and green. Okay, so right, so what I do is I just apply Gallai's theorem, right? So this says that my graph is a blow up of a 2-edge colored clique. So maybe it looks like this. I don't know, that's what that picture is. And there's some thick edges. So this, maybe all the edges between these blobs are red. Well, it doesn't matter if the picture's the same. So these are red, these are red. maybe this is blue. That's blue. That's blue. Maybe I'll use yellow because yellow is different than, maybe you can see the difference between yellow and green easier, but whatever, like. Okay, so you apply Gallai's theorem and you get this decomposition. So, right. So now you just apply induction, right? So I know that each of these guys can be partitioned into 3 cographs, right? So that's what that picture says. This. So the picture was a bit misleading because remember, each one of these guys is a spanning subgraph, but there's basically a red-blue subgraph. There is a red-yellow subgraph. Is that better? And then there is a blue-yellow subgraph in each of these guys. Okay. Maybe I'll just do this twice. Blue, red, red, yellow, and blue, yellow. And each of these is a cograph, okay? And then now all I need to do is to tell you how to lift these back to cographs of your big graph that decompose your original complete graph. And that is quite easy to do because there's only 2 colors that appear on the outside here, right? So what this means is that, say for the red-blue subgraph and this red-blue subgraph, I can just union them together using these red edges. And cographs are closed under this join operation, right? So if you take 2 cographs and you take a join of them, that's still a cograph. So this means that I can join this cograph with this cograph to produce like another cograph. So I'll do that for all of the red-blue guys. And then for these 2 guys, I'll just take a disjoint union, right? So again, the disjoint union of 2 cographs is still a cograph. So I just disjoint union all of the red-yellow guys together and all the blue-yellow guys together, right? So this is how you prove this theorem. Good. Okay, so now that we have this theorem, like let me prove Erdős-Hajnal for graphs for rainbow triangles, right? So okay, so let us apply this Fox-Grinspoon-Puck theorem, right? So I have these 3 cographs, G1, oh, sorry, yeah, I will wait. Okay, so I have these 3 cographs, the red-blue one, the blue-green one, and the red-green one, that partition my graph. So let's consider the blue-red one, G1, right? So I look inside G1. Remember, G1 is a spanning subgraph, so it has n vertices. And I just ask, well, what is the clique number of G1, right? So I'm aiming for n to the 1/3, right? So if the clique number of G1 is at least n to the 1/3, then I'm done because G1 does not use any green edges, right? So if I find a clique here, it will be homogeneous, right? So I know that the clique number of G1 is at most n to the 1/3, right? But now this implies that the independence number of G1 is at least n to the 2/3. And what am I using here? Just the fact that G1 is a perfect graph. So G1 is a cograph. In particular, it's a perfect graph, which means that if you take the product of the clique number and the independence number, you get something that's at least the number of vertices, right? So this is the only property that I'll use. So now I have this large independent set in G1, at least n to the 2/3 vertices. So what I do is now I look at, well, what does G2 do on this subset of vertices X, right? So now, again, if I find a large clique in G2 of size n to the 1/3, I'm done because G2 has no red edges. So I use the same argument. This means that I have an independent set of size n to the 1/3, right? Y. And so this set Y is precisely what I'm looking for because it's an independent set in G1, it's an independent set in G2, but remember this is a decomposition of the entire graph, so all of these edges are in G3. They're actually a clique, and G3 avoids blue. So this is the proof. So you get n to the 1/3. They actually prove more, so it turns out you can add a log factor to this. But in the geometric world, you don't have to do all this extra hard work to get this log factor. Like n to the 1/3 is actually the answer. So, so I encourage you to move to the geometric paradise, so you don't have to work with graphs. Okay, so right, so all of that was just inspiration. We do the proof kind of in exactly the same way. So we prove this Gallai's theorem, but for projective geometries. And if you only care about the this rainbow Erdős-Hajnal, you don't need the full structure theorem. So this is actually enough. So if so this is a weak version of Gallai's theorem. All it says is that you have a chain of subspaces, like starting from the empty subspace all the way up to the projective geometry that's well behaved, right? So, so it's well behaved in the sense that the number of colors that appears in the next subspace, but not in the previous subspace, is at most 2. Okay, so, so actually, once you have this, you can prove this rainbow version pretty easily. But we actually prove more. It's a bit technical to state this exact structure theorem. But it's completely analogous to Gallai's theorem. Okay, so our structure theorem has some nice consequences. It implies that there's actually a unique coloring. So if you use n colors in the projective geometry of dimension n, then you will okay. It's possible to not have a rainbow triangle, but there's only one way to do it. Once you use more colors than this, you'll always have a rainbow triangle, actually. So that's a corollary. That was already proved by these guys that proved a bit more, actually. Okay, so, right, so using this same proof method, you can get this epsilon equals 1 and beta equals 1/3, right? Okay, so let me maybe finish with some open problems as well. So again, like Erdős-Hajnal, we know that it only holds for a few graphs. We also saw that in the geometric world. So so we only proved it for these small values, but the punchline is that even for graphs, we only know it for small graphs. But it is true that you get something better than logarithmic for graphs. So it'd be nice to prove maybe not a polynomial bound, but any bound that's better than these geometric Ramsey bounds for these colorings. And yeah, so and anyway, there's like many like open questions you can ask in this area. You can see we didn't really do too much. So I think that's it.